Good morning, everyone. So looking at the room, I think I can have a more interactive session as well, because, yeah. Uh, so, low rank adapters. And it's something that you've probably heard a lot about in the last year and a half, because it has become synonymous with fine-tuning LLMs, right? Like any tutorial you'll open in the last year or so, it will be done with LoRa if you're going to fine-tune a model. Yeah. So what is it? How did we get here? And if you just step away from the landscape of LLMs, of multi-billion parameter models, there's a lot of value it can deliver to all of us here, because not all of us are training LLMs, but it's a technique that trickles down very well to not so large models. Okay, so what are we going to do? So the overview is that I'll just first right away off the bat give you the takeaways. We'll do a deep dive, and then a lot of benefits and impacts that at KBC, a Belgian bank, we've been able to derive in the last 1 year. And it's been quite phenomenal. It has allowed us to reduce the time that we spend on problems in general. Okay, so the takeaways. So the most common takeaway that you're already all aware of is that the modeling becomes a lot faster and very cost efficient. And that's why it has become so popular. The deployment becomes insanely cheap. And we'll do like a couple of use cases and case studies about how it affects your training, active learning pipelines, and then a very niche use case, which probably all of us here are suffering from GDPR expiry of data. So that's a problem every organization faces, and somehow this technique pays off very well there. And then in 2024, we can still make slides without AI-generated images. OK, so update dive. Sorry. So, so how did we get here? Because I think nothing happens in one night. Nothing happens as a moment of illumination. So first of all, there was the Big Bang. And then we spent all that time arriving to deep learning and transformers. So until 2019, we did that. And then in 2019, we have something called adapters. And that was sort of the start of this whole revolution. And then in 2020, some people at Uber figured out, that language models have a low intrinsic dimension. What that means is that only a small part of the model is actually effective. You're not using the whole model when you're training or fine-tuning. And then we arrive in 2021 at low rank adaptation. And it's 24, but the technique is actually quite old at this point. OK, so before we go in, I want to set some very basic premises that we're going to be using. And we'll be determining all the things that we extract from the talk or all the conclusions we will make. So most of the model's knowledge comes from pre-training. For text models, so all the LLMs that we know, that means their understanding of language and the factual knowledge is coming from the pre-training phase. For image models or CNNs, diffusion models, that's where they understand all the shapes, colors, edges, what all the objects are, all the semantic understanding of between things, like a head has to be above hands, for example. Right? So this is a very basic premise we need. And then LoRA is a technique that builds upon linear matrices or matrices. So it can be applied to attention-based models, CNN-based models, and what it also means, it is independent of the size of the model. So you can equally apply it to large models. So you can fine-tune maybe a Falcon 40 billion, a 500 billion parameter model, but equally you can fine-tune a 100 million parameter model using LoRa. Okay? And OK, so let's start. Adapters. OK, so we'll do a raise of hands quickly. How many times have you struggled in your career, if you're dealing with NLP or computer vision, that for the same problem, for different problems, you have to fine-tune the same model and deploy the same model over and over and over with just certain changes in the data set or whatever? Raise of hands, yeah. And what that also means is that you're spending a lot of money duplicating the same architecture, same weights. So this is where the idea of adapters was very influential. It was introduced in this paper in 2019. And maybe you get a hint of the library, Hugging Face library PEFT here as well. And the idea was that you don't have to fine-tune the whole model anymore. People were already doing that. Like, they were not fine-tuning the whole model, they were fine-tuning top layers. Because the idea is that all the base layers of the model are capturing the essential basic features, and the top layers of the model are capturing all the hierarchical interactions or the interactions for your task. So what they do is they capture new knowledge of your data set, your organization's data set or whatever, in a smaller set of parameters. And how does that happen? So this here is my original model. You inject some layers somewhere in between, and you freeze everything else, and you just train these adapter layers. And there's a lot of forms of those. It was quite big. And what happens is that the original model is still going to work the way it was, but these adapter layers are adapting to the different activations of your new data set. So the new knowledge is being captured here. But now think about it. You have the same base model. You want to deploy it. You actually have to deploy the base model once, and these adapter layers are your things that you can bring it at runtime, right? So you reduce the cost of deployment by quite a lot, but you're adding more parameters. So you need more inference time. You need more compute to make the same amount of inferences. But OK, this is anyways much better than what we already have. We're not deploying the whole model again. We're not fine-tuning the whole model again. Yeah. OK. And for almost no trade-off in performance. So you can add adapters up to like a few 10,000 parameters on a few 100 million parameter model. And if you fine-tune the top layers, which was a very standard practice at that point, even is now, you get better performance overall out of it. And that's purely because we'll get to see how that works, actually. Yeah. But yeah, the takeaway is that you can capture new knowledge in a smaller set of weights, and for no loss in performance. Your deployment becomes cheaper, and inference does increase a bit in latency, but that's OK. OK. Then what people figure out is that, I can fine-tune the same model, get exact same performance for a very small set of parameters, new parameters. So something is happening. So then what happens is that they figure out that deep neural networks have low intrinsic dimension. That means that only, a small set of parameters is used in the process of fine-tuning. Once the model is pre-trained, only a small set of parameters are actually effective. All the other parameters sort of can be ignored. Yeah? And what that means is if you have a matrix, only a small set of parameters will be useful. Everything else you can get rid of. And that is also the principle behind model pruning as well. You can get rid of the weights that you don't need. Yeah? And that's why also, I'm making an exaggeration, but dropout also works. Huh? OK. So what this can also be rephrased as that the task or the data set is compressed, the pre-trained knowledge is compressed in a few dimensions, not just in some parameters, in actually few dimensions along the model. So let's say my model was actually three-dimensional. Let's say I'm training a three-dimensional matrix. It will figure out a plane in my original subspace of weights, and everything happens just on that plane. So my model has learned to figure out, using the 3 dimensions of the original weights, that I can only do everything in just a 2-dimensional plane. And if you manage to extract it, voila, you're golden. You have managed to reduce the dimensionality of the model by a huge size. Huh? OK. OK. So what that also means is that the weights are probably not that scattered, the parameters. They are a bit more organized throughout the whole matrices of the model. OK? But then people are like, OK, this intrinsic dimension is very low, but how is it actually working? How can I actually leverage this? So there's this another paper which pre-trains LLMs sometime in 2020. And back then, LLMs were not still billion parameters. They were still a few hundred million. They were able to train a BERT model with 200 parameters and achieve the same performance as fine-tuning the whole model. So you take the original model, they projected the original matrices to a new space, and they just fine-tuned that space. And what they figured out after a whole analysis, so the projection that they made was they could trace this stuff back. And they figured out the pre-training process is actually reducing the intrinsic dimension. And model using all the other parameters is able to compress information in fewer dimensions. Now, how or why is this happening is pretty interesting, because if you go back to 1980s, you find out that that's when the cross-entropy loss is introduced. And what cross-entropy loss is doing is, it's trying to minimize the entropy. So it's actually trying to find the smallest way of describing a task, the minimum task description principle. So that's how these connections are made. And what we then figure out is that these intrinsic dimensions inside the original weights are the ones that are actually used during fine-tuning. So somehow during the fine-tuning, the model is able to say, you need, for example, in a text model, this piece of text has these pronouns and these nouns. And I have managed to capture that information in these set of parameters or these dimensions, and that's all you need. You don't need anything else. If your data set is more emotion related, you just work with those dimensions which capture the emotion. We don't know how that's exactly how it is, but for the intuition process. Okay? And the larger the model, the more hybrid and lower intrinsic dimensions does it have. So what that means is a GPT-2 with, let's say, 3 billion parameter models is having a lower intrinsic dimension. So it is able to compress more information. It is able to learn hybrid concepts for a simplification. Okay. Now, we're working with matrices. And what's the easiest way to minimize the number of parameters in a matrix is to minimize its rank. Yeah? So the matrices of models are low rank. That's something that we know now. And what is low rank? Who knows? OK, so that means that only few rows and columns of the matrix are actually unique. Everything else in the matrix can be derived using all these fewer columns. I have some visualizations later that will help with that. And the information is compressed into these smaller sets of rows and columns. OK, now we'll come to low-rank adaptation. OK, so the whole crux of everything that we do here, or what everybody who's training models is doing, using a pre-trained model, you have an original model that you got from somewhere, and you're just trying to find this delta W. That's all that is there to fine-tuning. Now, we can take this delta W, and we can represent it as like this. So these are the low ranks. So only these rows are effective. Everything else that is in black here is actually redundant. You can somehow arrive at these black rows using everything else in the matrix. So these are the only unique parts of the matrix. What you can do now is that, let's say this was M&M, and we want to do a parameter reduction. So we want to get rid of quite some useless information here. How can we do that? How do you reduce the number of parameters in a matrix? Any ideas? Sorry? Voila. So we have factorization. So what you do is, you take this original matrix, and somehow you figure out that this matrix can be broken down into two smaller parts. And what that means is, all of this area, all these parameters that were filled here are gone now. You no longer need them. You can just arrive at this matrix, take this matrix, break it down, and that's all you need. You don't need anything else. So that's also, for example, how singular value decomposition is also working to a degree. OK, so we have this matrix. So we took a delta W, our fine-tuned model. We broke it down into smaller parts. And let's say, for ease of visualization, let's represent it like this. So more information is coming in. So M or N is becoming lesser information. and a smaller set. So it's a funnel. And then we take this funnel again, and then we expand it again. Okay? And we're calling these matrices A and B. And our delta W is now a product of these two matrices. Okay? But again, deep learning comes in. But maybe we can just learn these matrices during the training. We don't have to fine-tune the whole matrix. If the decomposition works, maybe we can decompose beforehand and just let the model figure that out during the backpropagation process. Okay? So what we do in low rank adaptation is that you take your original model, original weights, you figure out B and A through some process, and then you fine-tune them together. So your input X is going to flow through your weights here, it's going to flow through your weights here, you're going to do a piecewise addition, and voila, that's your output of your layer. Yeah? And now, the original model you're using, it acts as a bias. Why? Because we only capture the weight updates in matrices A and B. So I'll have my weight updates come in. I will let them float through my low rank adapter. I will not let them flow through my original model. So my original model is frozen. I'm not doing anything to it. I'm just letting it affect my output, but I'm not updating it. So I'm not changing its behavior in any ways. And then, intuitively, we can understand that whatever is happening in our data set is being captured here. Okay? Okay. So, yeah. So a fraction of weights are trainable because of this process. And it can be as low as 0.002% of the original weights of your model. What that means is, this is a grid of 1,000,000 dots. And out of those 1,000,000 dots, you only need to train the green ones. And they have been magnified by a factor of 100 here. So that's all you need. Once you have a pre-trained model, that's all you need to update and fine-tune your model on your task. So just for a visualization, how little that is and how effective that is. OK, so what that also means is, at runtime, you will need less compute. Your gradient updates have to be performed on lesser number of parameters. So you need less GPU space. You can iterate a lot faster. So your training becomes very fast and very cost efficient. Yeah? So that's our first takeaway here. Now let's talk about inference and deployment. So I had a data set 1 that I captured in my delta W1. And that was 0.002% of the original weights, for example. I can do something very similar, and I take a data set W, D2, and fine-tune another adapter and put it on the side. I can keep doing this because these models are so small. For example, if you take a BERT model, I'm just going to use that as a baseline, an adapter trained on a BERT model is 1.2 megabytes with a rank of 8 or something, whereas a BERT model on its own is about 500 megabytes. So all you need now is that your whole data set is compressed in that 1 megabyte processor. So you can deploy n models for the cost of 1. And for us, it has paid off in a big way because it's a bank. So we have quite some models fine-tuned on some very base models. We were able to take all of those out. We got rid of the costs are about 20 times cheaper now, purely because we need one base model loaded in memory once, and you decide at inference which adapter you want to load. And that's the one you use at inference time. Yeah? But now let's think about something, where we are right now. We have managed to capture our data set in a smaller set of weights. And this addition here, that's what we're doing. It's happening within our control now. So we can actually amplify the output coming from my adapter. What that means is that I can amplify or diminish the impact of my adapter or my data set depending upon what suits my needs. This means you can actually maybe get a higher performance on your data set post-training just by augmenting the gamma values. So that's a hyperparameter you can play with. And yeah, you just make your data set knowledge shout louder, if that makes sense. Okay, cheaper deployment. So what I showed right now was, okay, I have a adapter and I have a model and I can just play with it. So let's say we take BERT model, which has 109 million parameters, and we make an adapter of rank 8, d dimension equal to 8. It's only 0.004% of the original parameters. That means you can deploy 246 models for the cost of 2 models. That's an absolute game changer. The amount of costs that you need to invest now is very low. Okay, but till now, we've been only doing one adapter inference at a time, like you choose at inference time which one you want to go through. But that's not true anymore. Through a lot of neat tricks using CUDA, people have been able to figure out how you can use all those delta Ws in one forward pass during inference. So thanks to Punica, I won't go into details, and LoRa X, what they do is, so they figure out very neat CUDA tricks. And what they're able to do is that you have fine-tuned model adapter 1, 2, 3, 4 till 32. The cost of deploying or cost of generating million tokens sort of remains the same. You're not investing any more in deploying new models, whereas this cost keeps on increasing because if it was an original way of fine-tuning, you would have to deploy the same model again and again and again. And yeah, your cost is going to rise, but with this method, your weights are very small. You can stack a bunch of them together. Doesn't result in any memory increase overall. And yeah, your cost remains the same. Okay, so we have our second takeaway of cheaper deployment. Okay, now some insights. Because, okay, now we understand that we had this delta W, and we were able to factorize it, get 2 smaller matrices, resulted in a, you see, like, there was the big chunk of matrix that was missing. So that was the parameter reduction we achieved. But what is actually happening? So we know, and how do we know is something different. Maybe after the talk, if you want to discuss and find out more, you can come to me, is that it borrows the most important dimensions of the model that are responsible for the task at hand. So if your data set is about emotions, for example, it will only borrow the compressed dimension that is representing emotions in the pre-trained weights. It will not borrow anything else. If your data set is, for example, about NER, it will, let's say, it needs to know difference between cow and a pig, for example. It is able to borrow the dimensions that represent those nouns and pronouns and whatnot. It doesn't borrow anything else. So it just augments the parts. And so if these are my, let's say, my original matrix, and these are my adapters, my adapter only borrows the combinations of these. It is not taking anything else. And that's rather remarkable. We don't know how it works, but we know that that's what happens. So let's call this the connoisseur property of LoRa. It's able to choose and select and keep in its pocket what it needs the most. Nothing else is important for itself. Yeah? Okay, but catastrophic forgetting. Because LoRa has been very much claimed in a lot of things that you read online, that it alleviates the problem of catastrophic forgetting. Who knows what that is? Yeah? Cool. So it just means that you have a model, you keep fine-tuning it, it will start forgetting the old things that it knew. So you probably have also experienced it with GPT, ChatGPT. Things that it was good at in the past, maybe it's not good anymore because the behavior changes. You keep update the model, it forgets past knowledge, and that is something true for every kind of model. It's not just this. So computer vision, NLP, even classical models have this problem to a degree. So LoRa is not updating the original weights of the model. So that means the original knowledge of the model is still there, captured somehow, and you're just using the information that you actually need in your delta W. So the model knowledge is not being overwritten. And that can be very handy for us. And LoRa amplifies the dimensions that it needs the most, and probably are not that important in W itself. So for example, my model learned a concept of emotions, it learned the concept of what is a cow, what is a dog, but for it, it's all equally important. But for my data set, it is not. So LoRa chooses something out from it, amplifies it by a degree, And then we can also amplify it using gamma. Okay? Now, what we also know is that larger the rank, the more directions are picked up. How that happens, we don't know, but it does. Now, I have two questions for you. Wait. Okay. If we want to measure the overlap between the original model and the delta W, so this is a diagram from the paper itself. So we have the matrix, and A here means the right singular matrix. Doesn't matter. We're seeing how much is the overlap between my original weights and the fine-tuned weights. And so rank 4, 8, and 64. Rank 64 has quite an overlap compared to other ranks, but it is carrying over information from the original weights and the original model. Okay, I have two questions. Do you think an adapter can learn new information? Can it learn something that is not already learned by the model? Maybe it can, maybe it doesn't. There's no clear way of knowing that, but your data set can introduce some things that were not part of your original model, but your model will still learn it out. So there is some behavior to that. Okay, we think that they're capable of learning new information, but yeah. Next question. Does the model plus adapter, we're not overriding the model, does it override the previous information? Can it do that? Yeah? So it can, very much likely, because let's say the original dimension of the model for, let's say, learning emotions was this direction. Your adapter can actually learn a vector in the very opposite direction for it. And it can override that information. But we don't know how that works, but it does happen. So now, benefits and impacts. I'm running a bit behind time, but incorporating LoRA in practice. So I think this is what is the main thing here. So as data scientists and ML engineers, it has a massive impact on the workflow because it helps you deal with noisy data. And there, we'll see how that works, but it's something pretty unique. Active learning becomes rather easy and straightforward, and dealing with GDPR expiry data, and freedom of having many models. I'll come back to that. And for ML ops, I won't dive further into this, but there's a cheaper deployment practice, and you can have the same backbone. So you can have a very standardized way of deploying models and working with them. Okay, dealing with noisy data. So we leverage two properties of LoRA. So first one is that it's a connoisseur. It captures the information that it needs and augments the directions it needs, and we can amplify it. Okay? So I suggest a method that I figured out. So we fine-tune the whole model. For example, let's take BERT. You're probably dealing with BERT. And we fine-tune the whole model on the noisy data. And then what we do is we fine-tune a very small amount of gold standard data. We fine-tune a LoRA adapter. Why? So, So what's happening is that when you're fine-tuning the whole noisy data, the model still learns the new patterns in your data set. And the top layers are being affected for your final task. And the patterns are now embedded into the model. So maybe some things that were not seen by the model before and whatnot. Yeah? But it's still noise. Your model is not going to perform very well, but somehow we managed to capture the information. And then what we do is we take a smaller amount of We take a small amount of gold standard data, and we fine-tune an adapter on that. So this data that was gold standard has very clear annotations. My adapter learns the behavior of those. Yeah? And we can amplify the impact of it. So now my model that has learned the patterns, but is noisy, I take my adapter, which has the correct information about my data set, knows what correct thing is. It amplifies that direction, and what you can get is something very amazing. So a small case study, model layout LM. Layout LM is a multimodal transformer that works for documents, and the input to the model is the layout of a document page or any page, and the text with every text associated with the document. The task is token classification. So what I want my model to do is classify the label of every bounding box on the page. So for documents, it could mean that you want to figure out the total amount, the name of a person, bank account, whatever, invoice. In insurance, it's very common. It's a custom data set because it's a data set inside the bank. So what I did was, I had my training set. I took 80% of my data, and I shuffled the labels. 80% of the labels, I randomly shuffled them. And then the 20% of the data, that was probably a bit noisy anyways, because in practice, it's very hard to get very clean labels. I sent it back to labelers and asked them to revisit the labels, so it was very clean labels at the end. So I fine-tuned the whole model on my noisy data set. The test F1 score is 23%. Okay? Then what I do is I take my gold standard data and I fine-tune my whole model. So 2 steps of training. I get a F1 score of 87%. But then I take LoRA and I have my base model fine-tuned on the noisy data, and I have my LoRA adapter fine-tuned on this gold standard small amount of data. And somehow it outperforms fine-tuning the whole model. Pretty remarkable. Why is that happening? I think it's because it has lesser number of weights, so it cannot overfit, and it has to capture the most, for a lack of a better word, the eigenvectors of my data set. So it is not capturing all the noise, but I can amplify the direction. So my model knows the data format, but my LoRA knows the correct label, and at inference time, my LoRA is able to shout a lot louder, and it says, you know something, I know something better, but we're gonna give this output because I can shout a lot louder and I know better than you. Parameter gamma. Okay. And here the dimension was 16, gamma was equal to 8. So you see like I'm amplifying the output of LoRA adapter by quite a lot of values. Your mileage may vary. I have not done massive studies on open source datasets and whatnot. I have spent some time. But this is a common pattern that we've seen across a lot of NLP tasks and a lot of document AI tasks. And for the whole year, it's been, we keep throwing stuff at it and it keeps delivering. Now, active learning. Who here has to deal with active learning as a big part of their jobs? Yeah? So, what is active learning? Sorry. Okay. So, it's coming up. So, the current method that we have is that we fine-tune the whole model on noisy data, and we fine-tune LoRA adapter on a small amount of gold data. Active learning means that you deploy a model, something changes, you come back, update it again, and you deploy it again. Okay? So my proposed method is this. We fine-tune the whole model, and then at the end, we have to fine-tune a LoRA adapter, right? So what you do is you extract the uncertain instances and label. So you don't have to spend a lot of time getting good labels for your initial training. Yeah? You train that model, and then on your training set, you go and ask the model what are the most uncertain instances. So for example, what that means is things that are very close to the decision boundaries. So in classification, that would mean for something that has a probability of 45% to 55%. That's the confidence interval. You extract those, you do a very focused labeling on those samples, and then you fine-tune a LoRA adapter on that. You can repeat this cycle. Yeah. So, for example, we take BERT. The task here is multi-label text classification, multi-label, multi-class text classification. Dataset is custom. And so we had an initial model that was trained. We had a batch 1 of active learning. So we extracted, the original sample size was 50,000 samples. We extracted 500 samples in batch 1, the uncertain instances from the training data. We sent them for very focused labeling. So the exact match ratio means that all the labels coming out from the model were as per the original labels. The LoRA adapter outdoes the model by about 5 to 6%. And that's a trend, and then we go ahead and do it for batch number 2. Then we go ahead and do it for batch number 3. And my adapter keeps outperforming, fine-tuning the whole model. And here these charts are, so I've done a whole parameter sweep on my hyperparameters of the original model, and a hyperparameter sweep on LoRA as well. So these are the best models I could have extracted for that data set. And if you also see that, so the starting point is already very massive, but for the last set of data set, the slopes are different between this point and this point for both the curves. So somehow my LoRA is able to capture something that my model is not, if I fine-tune the whole model. So what that means here is, I took my original data set that was 50,000 samples. I took approximate labels. Because in a business process, you will have those proxy labels very easily available. And in each of these, we totally only labeled 1,000 samples through the process of active learning. Like, give me the uncertain instances, I'm just going to fine-tune them, put them in an adapter, extract more, fine-tune them, put them in an adapter. I was able to extract a lot of value by labeling a fraction of the data in a very focused manner. So the amount of business hours that it saves everyone, especially in a big organization, is pretty massive. Okay. And yeah, for this exercise, the dimension was 32, and our gamma was 8. So we're trying to capture more information, and we're making the data set shout a lot louder. Okay, your mileage may vary. I have not done studies on open source data sets. I have not written a paper yet, but this is something that we've been seeing all throughout the year since we started using them in February. Okay, so what's going on? I've already touched upon this, but base model is learning the new patterns somehow in your data set. Even with noisy data set, the labels are different. Huh? That's the noise is in the top layers, and top layers are adapting to the task. And with LoRA and correct gamma, we can ask the model to repurpose its existing knowledge. That's how I try to look at LoRA. It's repurposing models' existing knowledge into fine-tune to your data set and your task. Okay, GDPR expiry. So, a life of a data scientist and MLE in Europe, you train an initial model, you deploy it, and you see data drift in production. You come back and update using active learning. You repeat the process 2 and 3 as many times as needed. But then what happens is, you had asked your customer for an initial consent on the data for maybe 18 months, 2 years, whatever. That has expired. You cannot use that data to train your model again anymore, right? So how do we still keep the performance alive on the expired samples? Because it doesn't mean that data is not going to show up again, right? So this is something that is called continual learning, where you keep learning new information. You put different domains of data in your model with each step of the problem. And the tasks are different now, because the data set looks different. Maybe the labels are the same, but inherently it's different. And yeah, you get a different model, but the model will start forgetting previous information. It's not going to be so performant anymore. So we can alleviate this through LoRA, and we can get an adapter for each step of the active learning process. So I'll skip this slide, and I'll quickly give you a visualization. So this is my pre-trained model, and for my dataset 1, I can have one adapter, dataset 2, dataset 3, and I can keep doing this process for a while. And it's super cheap, right? Deployment is not that hard. So how do we do this? So let's say my model is fx, yeah? And this is the output range of output domain of my model, okay, this circle. I take few samples from each of my data sets, and I embed them into the space of the model, the original model. And then for each of those things, I have an adapter. And then I have a new sample h come in for inference. I'm going to embed the same sample into my output domain. And I apply k-means, and then I see that this sample is actually closest to this specific data set point. And then I just infer using that adapter. And this works very well in practice. This has allowed us to not bother so much about keeping all the data together, like dataset versioning and stuff. Like, it all becomes rather easy. OK, is there more? There is. So getting a new model is now cheap. It doesn't cost any memory. It doesn't cost any extra deployment time. And training it is faster as well, and you can train it with a small number of samples. But we can make them all work together as well. What does that make you think of? Ensembling. Yeah? So you can, for the same task, get a bunch of adapters, and you can ensemble them together as well, because they're all so cheap in memory now, so cheap for inference. And so you can do a horizontal stacking of them, or you can do a vertical stacking of them as well. And this paper called Mini Ensemble LoRA does a very neat trick. So it puts them all together. So your original dimension is D, and it just fills the diagonal of the matrix. So it just has smaller adapters along the diagonal for both A and B. And somehow there's a lot of explanation, but it is able to outperform the original LoRA as well. So ensembling is a big, powerful thing that also comes out of this thing, because model is cheap now. So that's the idea of all the takeaways and the expired data and la 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 la. I do have to put some word dimensions because the whole LoRa movement began a series of new techniques to come out. So of course, one of them is called DORA. Um, and in DORA, what they do is they decompose your original or your delta W in a direction and a magnitude matrix. So they're not just doing B and A, but they put it in a direction and magnitude, and then they fine-tune the direction and the magnitude independently. And then you have, of course, LoHa, which in Hindi means iron, but it's a low-rank Hadamard product. And then QLoRa, quantized LoRa. So what we can do it's also the most popular technique that you'll see whenever you go out online to fine-tune a model, is you quantize the pre-trained model, 8-bit, 4-bit, it's up to you, your mileage, and you add a LoRa adapter to the quantized model. Now we know that quantization does not get rid of the dimensions or the knowledge of the original model, but LoRa is still able to learn your data set. Okay? And yeah, there were no AI-generated images in this talk. And yeah, thanks for your attention and questions.